At Spirit the Kid said. Test.
At Spirit the Kid said. Test.
At Spirit the Kid said. Test.
Hello. Bro, I don't fucking know what I'm doing at this point, bro. At this point, bro. Oh yeah, I forgot. These are the word. Oh. What was I? I'm just gonna do blunted, fuck it. Damn. Damn. Fuck. Damn. Anyways. Holy fuck, I hate these wires. I'm fucking gay. Holy shit. Shit like this is ass. Alright. Yeah, I'm lucky. I just want to get, like, 35 plus on this level. As I fucking... I am so ass. Damn. Why? Second time, by the way. Okay. Damn. Why is no clip enabled? What the fuck? Last attempt at getting off of this. I'm playing Aftermath. This is ass. I was supposed to verify this shit like a month ago. Yeah, just suck my fucking cock. Oh yeah, okay. What the fuck? Okay. Okay. Yeah. Love to see it, bro. We love to see it, bro. Yeah. Bro, I love having my wave as my fucking cube. Like, what? Bro, holy fuck. You know what? Wave spell. What the fuck am I typing? 679. I'm so funny. Oh, wait, what? Nope. I mean, that was easy. That was easy. Okay. Okay, this is... Whoa. Hold on. Wait, hold on, hold on. What the fuck am I doing? Alright, let's go. That's all I had to do, bro. I'm saving that shit, bro. Shit ass. What the fuck? Okay, 330, bro. This is not wave. What the fuck? Oh, fucking get the fuck out of here, man. Copyable, man. Nah, you're chilling. Oh, I was gonna exit out. I didn't want to beat it. Practice. I'm dead. I already don't like this, man. Do all of that just to die there. Okay, just shut the fuck up. What the fuck? Okay. Yeah. Yeah. Okay. Okay. 552, I guess. Yeah. Like that. You're chilling, bro. Fuck, man. That's just low-key fun. Gotta do that shit again. Run that bag. Alright, enough, bro. Yeah. You're chilling, bro. Where the fuck? Hey. Okay. No. Okay.
At DanY9L2L said, hello.
Yo, what's good?
At DanY9L2L said, do 134467761.
I bet. One, 3, 4, 4. Bet. I bet. Accurate hitbox. Fuck, bro. Yeah. Yeah. Okay. Oh, I'm just gonna play the whole level. Fuck it.
At DanY9L2L said, this possible with accurate hitboxes?
I don't fucking know, bro. Oh no, Miku circles, bro.
At DanY9L2L said, complete idiot very short level.
Hold on. Bro, I will be right back. Chat, I'm back. Let's fucking go, bro. Bro. even hit that, bro? What? Trolling. Alright, but after this, we gon' play, we gonna play Aftermath, man. Fuck this. Alright, hardest spam ever. We'll see about that, bro. Yep, that is the hardest spam ever. Okay. You got that, bro? You got that? You got that? Yeah, okay. Damn, the music kind of just stopped. Kind of lonely now. As I die, okay. Hold on.
But design.
I love space. It's so interesting and mysterious and cosmic and huge. So let's cover an iceberg about
Ketchup
it.
chips.
This one's been requested a lot, and after the Ocean Mysteries iceberg, I thought it's finally time for me to do this. Let me know in the comments what you want to see next. Be sure to follow my Instagram, join the Discord, we can hang out, and most importantly, subscribe to the channel. I want to reach 500k by the end of the year. We might not be able to do it, but it'll make me so happy if we do, guys. Okay, straight into the iceberg. Starting in layer 1 with space has no sound. Sound waves need a medium like air or water to travel, and space is almost a perfect vacuum. That means there aren't enough particles bumping into each other to carry the vibrations we perceive as sound. Astronauts outside the ISS, for example, wouldn't hear an explosion happening a few feet away. That said, certain regions of space, like dense gas clouds or plasma fields, can carry pressure waves that scientists translate into sounds. NASA has even sonified data from black holes and nebulae. Not because you'd hear it in space, but because the frequencies could be shifted into audible ranges. And also, before we get too far, I'm just gonna go ahead and mention now, just for those who don't know, an iceberg works by, we're gonna cover the pretty basic stuff and the disturbing and mysterious stuff as we go on, so stay tuned. Pluto is just a planet. Pluto was discovered in 1930 by Clyde Tombaugh, hailed as the 9th planet of the solar system. For decades, it held that title despite being smaller than Earth's moon. But in the 1990s and 2000s, astronomers began finding other objects in the Kuiper belt, some nearly as large as Pluto, like Eris. This forced the International Astronomical Union, or IAU, in 2006 to define what a planet actually is. Their definition required that an object A orbits the sun, B is spherical, and C has, quote, cleared its orbit of other debris. Pluto fails that last test, so it was reclassified to a dwarf planet. The backlash was huge. To the public, Pluto had always been the underdog planet, small, far away, and beloved in textbooks and pop culture. Scientists like Alan Stern, who led NASA's New Horizons mission, argue that the IAU's definition is flawed and too Earth-centric. They point out that Pluto is geologically active, has an atmosphere, and should count as a planet in its own right. The debate continues even today. For many people, saying Pluto is a planet is more of an emotional stance than a scientific one. The sun will die someday. Our sun is about 4.6 billion years old, roughly halfway through its life cycle. It steadily fuses hydrogen into helium, but eventually that hydrogen will run out. In about 5 billion years, the sun will swell into a red giant, engulfing Mercury and Venus, and maybe even Earth. After that phase, it will shed its outer layers into a planetary nebula, leaving behind a dense white dwarf that will cool for trillions of years. The mystery isn't whether this will happen, but exactly how violent Earth's end will be. Some models suggest our planet might be consumed by the sun, while others say it'll just be roasted into an uninhabitable husk. Either way, humanity won't be around to see it unless we've long since left the solar system. Exoplanets. For most of history, no one knew if planets existed beyond our solar system. That changed in 1992, when astronomers Alexander Volkskin and Dale Frail discovered planets orbiting a pulsar. Then, in 1995, Michael Mayer and Didier Queloz confirmed the first planet orbiting a sun-like star, 51 Pegasi b. Since then, technology like the Kepler Space Telescope has revealed thousands of exoplanets across the galaxy. These discoveries shattered our old assumptions. Many exoplanets don't look anything like our neat solar system. There are hot Jupiters orbiting scorchingly close to their stars, super-Earths bigger than our own planet but smaller than Neptune, and even worlds that may be covered entirely in oceans. The sheer diversity suggests that planetary formation is far more chaotic than we once thought. The search for exoplanets is closely tied to the hunt for life. Astronomers look for planets in the habitable zone where liquid water could exist. A handful of promising candidates like Proxima Centauri b or the TRAPPIST-1 system have fueled speculation that Earth-like worlds may not be rare. What makes exoplanets mysterious is not just that they exist, but that we can only study them indirectly. Most are too far away to image directly, so astronomers infer their presence from wobbles in a star's light or tiny dips in brightness as a planet passes in front. Every discovery hints at an unseen landscape that, for now, is hidden from us. Black holes. Black holes are one of the most extreme objects in the universe. They form when massive stars collapse under their own gravity, compressing all their matter into a singularity, a point of infinite density. Surrounding that is the event horizon, the boundary beyond which not even light can escape. The very idea breaks common sense. Space and time themselves are warped so drastically that the laws of physics seem to bend. They were predicted by Einstein's general relativity in 1915, but for decades they were treated as mathematical oddities rather than real objects. In the late 20th century, evidence began piling up. Stars orbiting invisible companions, X-rays streaming from matter being devoured, and eventually the Event Horizon Telescope's 2019 image of the black hole in galaxy M87. The mystery isn't just their existence, but what happens inside them. The singularity defies known physics. Quantum mechanics and relativity don't agree there. Do black holes destroy information, or is it preserved somehow, as Stephen Hawking once debated? The information paradox remains one of the biggest open questions in science. Black holes also aren't just endpoints, they shape galaxies. Supermassive black holes, millions to billions of times the mass of the sun, sit at galactic centers and seem to regulate star formulation with their energy jets. Their sheer scale raises another question. How did they grow so fast in the early universe? Even stranger, black holes might not be permanent. Hawking radiation suggests they can slowly evaporate over unimaginable timescales. If true, the universe's future could not end with fiery explosions, but with black holes quietly fading into nothingness. Age of the universe. Figuring out how old the universe is has been one of cosmology's central puzzles. Using the expansion of galaxies discovered by Edwin Hubble, scientists realized the universe had a beginning, the Big Bang. Measuring the rate of expansion, the Hubble constant, and comparing it to the cosmic microwave background, researchers have estimated the age at about 13.8 billion years. But even here, there's controversy. Different methods of measuring expansion give slightly different numbers, a problem known as the Hubble tension. Some studies suggest 13 billion years, others over 14. The disagreement could mean our models are missing something, perhaps new physics or unknown particles affecting cosmic evolution. This uncertainty is why the age of the universe remains not just a number but a mystery. It's the foundation for every other timeline in astronomy, yet the exact figure is still debated by some of the brightest minds in the field. Center of the galaxy. Astronomers have found that nearly every large galaxy harbors a supermassive black hole at its center. The Milky Way's is called Sagittarius A, weighing about 4 million suns. Some galaxies host black holes billions of times larger. These central giants likely grew from smaller black holes formed early in cosmic history, feeding on gas, stars, and even merging with each other. The relationship between galaxies and their central black holes is still mysterious. Black hole activity can power quasars and active galactic nuclei, pouring out more energy than entire galaxies. Yet they also seem to regulate star formation. This feedback loop suggests that galaxies and their central black holes co-evolve, but the details of how that happens remains unclear. Laika. Laika was a stray dog from Moscow who became the first living creature to orbit Earth. In 1957, the Soviet Union launched her aboard Sputnik 2, a mission rushed to coincide with the 40th anniversary of the Russian Revolution. The spacecraft wasn't designed for recovery, meaning that Laika was never meant to return. Soviet officials initially claimed she lived for several days, but later reports revealed she likely died within hours from overheating and stress. The mission was controversial from the start, criticized as inhumane, but it also captured global attention. Laika became both a symbol of scientific progress and a tragic reminder of its costs. Today, Laika is remembered with statues and memorials in Russia. Her story marks an important moment in the space race, highlighting the sacrifices made, both human and animal, to push the boundaries of exploration. And with that, guys, that is the end of Layer 1. I kind of just got some pretty basic ones just to get us into it, and now we're going to get into the next layers, Layer 2, the tyranny of the rocket equation. So, Tsiolkovsky first laid out the math of space travel in 1903, in what has become known as the rocket equation. It's simple at first. The velocity that a rocket can reach depends on the exhaust speed of its fuel and the ratio between its total starting mass and its final mass after the fuel burns off. But the deeper you look, the more depressing it becomes. Add more fuel and the rocket gets heavier, which means you need more fuel just to move that extra weight. The cycle feeds in itself until you realize most rockets are basically giant flying gas tanks with a tiny payload on top. That's why people call it the tyranny. The math itself rules over what's possible. Staging rockets was the hack that we developed to deal with this. You throw away the empty tanks to get lighter mid-flight. Without staging, missions like Apollo 11 could never have even left Earth. Even today, launch vehicles like the Falcon 9 or SLS are fundamentally fighting against the same curve. The equation also explains why interstellar travel is so daunting. Chemical rockets can get us to the moon or even Mars with difficulty, but anything beyond that starts to break under the tyranny. To really break free, engineers look to nuclear propulsion, solar sails, or exotic concepts like antimatter drives. Until then, every launch is just a reminder of how limiting basic physics can be. Next entry is historic supernovae. In ancient records, sudden new stars would appear in the night sky, sometimes bright enough to be seen in daylight. These were supernovae, though observers didn't know it at the time. The Chinese recorded one in 185 AD, considered the oldest confirmed supernova. But the most famous historic case came in 1054, when a star exploded so brightly it was visible during the day for nearly a month. Today, we know that event produced the Crab Nebula, still glowing with its pulsar at the center. European astronomers also contributed to the record centuries later. Tycho Brahe described the new star of 1572 in detail, and his observations helped overturn the Aristotelian belief that the heavens were unchanging. Kepler's supernova in 1604 reinforced the point. Stars could die and the universe was dynamic. These events reshaped not just astronomy but philosophy, since the cosmos was no longer thought of as eternal and perfect. Modern science has been able to match up these written accounts with physical remnants in space. The Crab Nebula's expanding filaments line up almost exactly with the timing of 1054. Other remnants like Cassiopeia A point to supernovae that either weren't well recorded or were missed entirely. The mystery that lingers is not whether these explosions happened, but why they occur in slightly different ways. Some stars collapse into black holes, others leave neutron stars, and some fizzle as failed supernovae. Even now, astrophysicists can't predict with certainty which massive stars will go out in a blaze versus which will just collapse quietly. Stellar classification. When astronomers started cataloging stars by their light, they noticed patterns in the absorption lines of their spectra. This led to the Harvard classification system, O, B, A, F, G, K, M. From the hottest blue-white giants down to the coolest red dwarfs. It looks random, but it's based on how the early system was reorganized once scientists realized temperature, not hydrogen content, was the key factor. Our sun, for example, is a G-rated star. The classification unlocked a huge mystery: why stars look different colors, live for different times, and die in different ways. It gave us the Hertzsprung-Russell diagram, which basically maps out stellar evolution from birth in a nebula to death as a white dwarf, neutron star, or black hole. TV static. Back when TVs used analog signals, if you turned to a dead channel, you'd see that fuzz of black and white snow. A tiny percentage of that static, about 1%, actually came from space. Specifically, it was the cosmic microwave background radiation, the afterglow of the Big Bang itself, still echoing across the universe. The fact that everyday living rooms unknowingly contained traces of the universe's origin is one of the coolest space facts. Two radio astronomers, Penzias and Wilson, discovered the CMB in the 1960s while investigating what they thought was interference in their antenna. That radiation is now one of the most important clues we have about the early universe, mapping how matter clumped together to form galaxies in the first place. Cosmic rays. Cosmic rays are high-energy particles, mostly protons, that slam into Earth from outer space at near light speeds. When they hit the atmosphere, they create showers of secondary particles that rain down on the surface. Some even pass through our bodies every second without us noticing. They were first detected in the early 1900s by balloon experiments, proving that radiation was coming from space and not just the Earth itself. The real mystery lies in where the most energetic cosmic rays come from. Some clearly originate from supernovae, while others may be accelerated by black holes or neutron stars. But the highest energy rays, so powerful they make our biggest particle accelerators look weak, don't match up neatly with known sources. Astronomers still debate whether they're products of distant galaxies, gamma ray bursts, or something even stranger. Cosmic rays also pose a practical problem for space travel. They can damage spacecraft electronics, mutate DNA, and increase cancer risks for astronauts. Shielding against them is not easy since their energy allows them to penetrate most materials. Solving the mystery of their origins might also help us solve how to survive them. Micrometeorites. Earth is constantly bombarded by tiny fragments of rock and metal from space. Micrometeorites. Unlike the big, rare meteorites that make headlines, these are microscopic 2 mm sized particles, billions of which fall to Earth every day. They mostly burn up in the atmosphere, but some survive and settle in places like Antarctica or the ocean floor. What makes them interesting is the information they carry. Micrometeorites are basically samples of the solar system delivered free of charge, preserving materials from asteroids, comets, and even interstellar dust. Studying them gives scientists clues about how planets formed and what chemical ingredients were present in the early solar system. For astronauts, though, micrometeorites are a hazard, traveling at tens of thousands of miles per hour. Even a grain-sized particle can puncture a spacesuit or a spacecraft wall. The Kuiper Belt. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies extending about 30 to 55 astronomical units from the Sun. It's like a second